All right. As we discussed, one of the main sources of many ODEs in real-life applications is Newton's second law of motion, F equals ma. And in this example, again, we're going to see how an ODE arises from applying Newton's second law. Specifically, we will use our model to determine something known as the escape velocity of a rocket that is projected away from the Earth in a direction perpendicular to the Earth's surface. Let's see what our example looks like. Here it is. A body of constant mass m is projected away from the Earth in a direction perpendicular to the Earth's surface with an initial velocity v0. Assume the force due to Earth's gravitational field is the only force acting on the body. So this is a key assumption. In particular, we are assuming that there is no air resistance. But take into account the variation of the Earth's gravitational field with distance. So as opposed to many other examples that we assume that the force due to gravity is constant, it is mg, here we want to be more careful about the gravitational force. And we will be careful, as you will see. So let's see what the problem is asking us. Find an expression for the velocity during the ensuing motion. So one of the key things that we want to find is the velocity. We want to know what the velocity is at any stage during this motion. Find the initial speed that is required to lift the body to a given maximum altitude h above the surface of the Earth. So what should be the initial velocity v0 in order to make sure that this rocket will rise up to the level h, height h, altitude h, and that will be the maximum altitude, and then it falls back to the Earth. And then finally, find the least v0, find the least initial speed for which the body will not return to the Earth. In a sense, find v0 such that this maximum altitude h becomes infinity. There will be no finite maximum altitude. Such a v0 will be called the escape velocity, the v0 that will ensure that the maximum altitude h is infinity. There is no maximum altitude that after that the object falls back to the Earth. Okay. So let me make some general comments, and we will solve this problem together. If you want, you can pause now, think about it, and then come back, watch the rest of the video. So the first thing is that, as it's clear from the statement of the problem, the question is about the motion of a body of mass m. So immediately, Newton's second law of motion comes to mind. I know that I have to apply the Newton's second law of motion. And as we discussed previously, every time I want to apply the Newton's second law of motion, first I will set up a coordinate system, and then I will draw a free body diagram, and then a diagram that shows all the forces that are exerted on the body of interest, the mass of interest, the mass whose trajectory is of interest to us. So let me do the job. So the situation that we have here is that we have the Earth, obviously. Here is the Earth. Okay, right. And then we have a mass m that is projected away perpendicular to the surface of the Earth. Maybe at time t, it will be somewhere here, right? The motion is perpendicular to the surface of the Earth. The only force that exists here is the gravitational force, which is perpendicular. There is nothing happening in the other directions. Nevertheless, I'm going to set up a coordinate system that has the x-axis, y-axis, and the z-axis. So this will be my x-axis. And then the y-axis, I'm going to choose it to point away from the center of the Earth, perpendicular to the surface of the Earth in the direction of motion of this mass m. So this will be my y-axis, y-axis. As a matter of fact, in this problem, as we will see in a moment, in order to be careful about the force due to gravity, I have to consider the radius of the Earth, and I will explain that shortly. So let's say that this is the center of the Earth, and then this is the radius. I'm modeling Earth as like a sphere. It has a radius r. I will give you more information about the value. There is a value for this radius of the Earth. So this is r. This is also r. This will be the center of the Earth. The center of the Earth. Of the Earth. We can also have our z-axis, but again, nothing is happening along x-axis and the z-axis. All the interesting things are happening along the y-axis. Here, the motion is in one direction, is a one-dimensional motion. Let me also, so this is, for example, at time t, your mass is at height y of t. Right, y of t. So the way I set up my y-axis is points away from the center of the Earth along the line of motion with y equals 0 lying on the Earth's surface. So let me actually, I can be I can write this down so to avoid any confusion. The way we set up our coordinate system is such that the positive y-axis points away from the center of the Earth, center of the Earth, along the line of motion of our mass, along the line of motion. With y equals 0, the origin, with y equals 0, lying on the Earth's surface. On the Earth's surface. So that is how I set up my coordinate system. And also before drawing the free body diagram showing you the forces that are being applied to this mass m, let me introduce the notation that I'm going to use for the position and the velocity and the acceleration of this mass m. So position, I'm going to use the vector r of t. Again, since the motion is along one line, it's in one dimension, we can represent velocity, position, acceleration, and force using signed numbers, but I prefer to work with vectors. I think it will make things easier when we work with vectors. So r of t here is equal to, it is in along the y-axis, the unit vector in the direction of the positive y-axis is j, and then the coefficient here, I'm going to denote it by y at t. So this is what I will call the position vector. And here the motion is in one dimension along a line. Sometimes people call this the position. When you have a one-dimensional motion, you can call the vector the position vector, or you can call just y of t the position function of the mass m. And then what will be the velocity? Again, the velocity vector, but I have to take the derivative of the position vector, which will be dy dt j. I'm going to denote dy dt by little v of t, as I did in other problems, v of t. So here, little v of t is the derivative of, little v of t is the derivative of y with respect to t. And then what will be the acceleration? Acceleration at time t, the derivative of the velocity vector, it will be j, and then it will be multiplied by a of t. I'm going to use the symbol a of t without arrow on top. This is a number. It can be positive or negative in general. And then this a of t is equal to dvt, the derivative of v with respect to t. Again, notice that when we have a motion in one direction along a line, sometimes people refer to these scalar quantities, to these numbers, as velocity and acceleration, instead of referring to the vectors as velocity and acceleration. Generally, velocity, position, acceleration, they are vectors, right? But when we have a motion in one direction, sometimes we use the term velocity or acceleration for these guys that you see on the right-hand side. Okay, and remember, just a reminder for everyone, this j is the unit vector in the y direction. So j is equal to 0, 1, 0. Okay, that is what j is. All right, so I set up my coordinate system. I did introduce the symbols that I will be using for position, velocity, and acceleration of the mass m. And the main question, remember, was about the velocity. So this v is of interest to me here. And now another thing that I need to do is that I need the free body diagram. That means that I need to look at the mass m and display all the forces that are acting on the mass m. In this problem, according to the statement of the problem, we are assuming that the only force that is acting on m is the force due to gravity, the gravitational force from the earth, right? The earth's gravity. So I'm gonna use a different color to show you how this force acts on the mass m. It will be downward towards the center of the earth. So Fg, and this is my notation for the gravitational force. Folks, typically when we are close to the surface of the earth, we assume that the force due to gravity is constant, mg, m times g, where g is acceleration due to gravity, 9.8 something, right, meters per second squared, right? That is when we are close to the surface of the earth. That is a good approximation. But here in this example, we are asked to not make that simplifying assumption that the force due to gravity is constant. So the question now is, well, what is this Fg? How can we compute this Fg? What is the formula for the force due to gravity? And to answer that, I need to remind you of a very important law, which is called the Newton's law of gravitation, or Newton's law of universal gravitation. It tells us when we have two masses, what will be the attractive force between the two masses. So let me remind everyone of that law, and then together we will, using that law, we will find an expression for this force Fg, which is the only force that is exerted to this body of mass little m. So reminder for everyone, I want to remind everyone what Newton's law of gravitation is, which is about the attractive force between two bodies. So I'm gonna write note, according to the Newton's law of universal gravitation. So previously I carefully introduced Newton's second law of motion, but I don't remember talking about the Newton's law of gravitation. And now I'm gonna tell you what it is, or maybe reminding you what it is. Most likely you have seen this in your other courses. The magnitude of gravitational force acting on the body here, I mean the body of mass little m that we have here, which is its weight, which we call its weight, the gravitational force from Earth acting on this body of mass m, little m, which is its weight, is inversely proportional to the square of its distance from the center of the Earth. From the center of the Earth. Awesome. So let me make one comment about this, and then we will see how this will help us to determine Fg in our picture, the force Fg, the force due to gravity that is applied to the mass little m. So the way I wrote Newton's universal gravitation, I just wrote it for the specific scenario that one of the masses is the Earth. But this law, the Newton's law of gravitation, is more general. Generally, it says that if you have a mass, big M, and another mass, little m, there will be an attractive force, and the direction of that attractive force, look at the center of mass here, center of mass there, connect that with a line. That force, the direction will be along this line. It will be attractive. The mass big M wants to attract the mass little m. The mass little m wants to attract the mass big M. And the magnitude of this force, so this is a general fact, not just for the Earth and the body that we are interested in here, for any two masses, little m and big M, according to the Newton's law of universal gravitation, the magnitude of the force will be equal to some constant g. I will tell you what the value of this constant is. This is a physical constant. It's a number. It's a known number. Times little m times big M, the mass little m, the mass big M, divided by the distance squared, the distance between the center of masses squared. This is the magnitude of the force between the attractive force, the gravitational force between these two bodies. Now, in the case that we are interested in, this big M, in our example, this big M is the Earth. And this little m is the body of interest, maybe a rocket that was projected away perpendicular to the surface of the Earth. So this is the situation that we have here. And what is the distance between this r in our case? Let me scroll up. In our case, the distance between the mass m and the center of the Earth will be equal to r plus yt. That little r that we had in this formula, the little r that you see in this formula, in our case, is the radius of the Earth plus yt, That r plus yt is the distance between the center of the Earth and the mass m. So they're putting all these together. Now I know what my Fg is. So let me actually put this note inside the box. This was just like a review. And then I can write a formula for my Fg. Fg, the force that is applied to the mass little m due to gravity, will be equal to G, which is a physical constant. I will tell you about this value later, but it's some number, some fixed number, times little m times big M. As a matter of fact, let me use big M subscript E. This is the mass of the Earth. I will tell you its approximate value later. Mass of the Earth, divided by y of t at time t, the distance from the surface of the Earth to the mass is yt, and then of course I have to add r. Let me actually call it re, so that it represents the radius of the Earth. Y plus re squared, so this is radius of the Earth. I will tell you its approximate values later. Radius of the Earth. These are known numbers. M-E-R-E, they are known numbers. Radius of the Earth. And just to make sure that everything is consistent in this presentation, so I'm gonna put the subscript E here as well. R in my picture, in my diagram, RE. This is the radius of the Earth. Okay, now going back here. So this is the magnitude. And what is the direction of this force? Now I have the magnitude. What is the direction? It points in the negative y direction. So I'm going to put negative J. Negative J. Now I have my vector. This is the vector that represents the force due to gravity applied to my body of mass, little m. And of course, so this is a generalization of what you knew very well. Because if somebody asks you, what is the force due to gravity? You immediately say it is mg, right? The force due to gravity applied to the mass m is mg. But this is when you are on the surface of the Earth. This is a more general situation where you look at the variation of the force based on the distance from the center of the Earth. So as a matter of fact, so what you know is that if yt is zero, if this yt is zero, then this magnitude that you see here, that is equal to fg. We know that, let me actually write this, we know that when y is zero, we have this magnitude that you see here is mg, g, m, the little m times the mass of the Earth divided by 0 plus the radius of the Earth squared. This must equal to the known value mg. You all know this known formula mg. That is when you're on the surface of the Earth. That is how you should think of g, the acceleration due to gravity. So as a matter of fact, this formula, this immediately tells me that g, the constant g times the mass of the Earth is equal to the acceleration due to gravity, which is 9.8 something, the value in meters per second squared, and then r e squared. So this is actually something interesting to know, right? We use the fact that on the surface of the Earth, the magnitude of this gravitational force must be equal to mg, and that tells us this beautiful relationship that actually you can use, for example, to see what little g is. What we know little g is 9.8 meters per second squared. Now, now that actually I know this, let me rewrite my fg. So we may write this force. Let me write it in terms of quantities that we are more familiar with, namely this little g. F sub g. This sub g is g stands for gravity. F gravity, the force due to gravity, is equal to, instead of GME, I'm going to replace GME with GRE squared. So I'm going to write the negative, we had the negative sign, mg RE squared divided by YT plus RE squared J. Very good. So just to be very, very clear, this negative J part is telling me that the force is pointing downward in the direction of negative y-axis. And I want you to all notice that this is a generalization of the formula that you knew before. Previously, you were all aware of the fact that the force due to gravity is m times g, little m times g. But that is when you're on the surface of the Earth, right? And here we have like a generalization of that formula. I want you to notice that when y is 0, you get your old formula back. So this is a check, like sanity check. Yes, this formula is working. When y of t is 0, when I'm on the surface of the Earth, this will give me the mg that I knew about. Okay, this is very good. Now I developed a formula for the force due to gravity, which actually considers how the force changes as we were moving away from the surface of the Earth, from the Earth's surface. Or now that I know my free body, I have my free body diagram. I know the force that is applied to my body. What I will do is that I will apply the Newton's second law to derive the equation of motion. Remember, that is how you always work with Newton's second law. You choose your coordinate system. You draw a free body diagram, make sure that the forces applied to the body are clear, and then you apply the Newton's second law to derive the equation of motion. So according to Newton's second law, let me actually change the color. According to Newton's second law, according to Newton's second law of motion, second law, we have mass times acceleration of the rocket, of that body that we projected away from the surface of the Earth, is equal to the total force applied to the body. Here, the only force that is applied to our body is the force due to gravity, which we denoted by Fg. So what does this tell me? That this tells me that ma of t j, remember, let me actually scroll up. Let me scroll up to show you our symbol for acceleration. The acceleration vector is a of t j. And of course, a of t is the derivative of v of t with respect to t. So I'm going to scroll back here. A of t j is equal to, what was our fg? I have it here. I have it 2 lines above. So this is negative mg re squared divided by y of t plus re. Remember, re is the radius of the Earth, squared j. So this immediately tells me that ma of t is equal to negative mg re squared divided by y of t plus re squared. And obviously, the little m on the left, the little m on the right, they cancel each other. So we get a of t is equal to negative g re squared divided by yt plus re squared. Okay, this is beautiful. And now, what was the quantity of interest? The quantity of interest was the velocity. So I'm gonna, the a of t is the derivative of v of t with respect to t. Therefore, the derivative of v of t with respect to t is equal to negative g re squared divided by yt plus re squared. Okay. So this is very, very good. Now I have an equation. The v of t is appearing in this equation. This is moving in the right direction. The problem with the equation that we see here is that here, v of t and y of t, they are both appearing in the equation. The question is not just about v of t. I have both v of t and y of t. So how can I deal with this? There are 2 ways now to deal with this. So one way that you may think of, which is a legitimate way to think about what's happening here, you would say that this v of t is the derivative of y of t with respect to t. So one approach here is as follows. One approach is that notice that v of t is the derivative of y of t with respect to t. So what you have on the left is the second derivative of position with respect to time, which is not a surprise. Yes, acceleration is the second derivative of position with respect to time. And then on the right, you have negative g re squared divided by y of t plus re squared, which is a second order ODE, second order ODE with the unknown y of t, with the unknown y of t. And what will be our initial conditions? The initial conditions here is that at time t equals 0, the position of the projectile is it is on the surface of the earth. Y of 0 is 0. What is the velocity? The velocity y prime of 0 is equal to v0. The initial velocity is v0. So one way to deal with this problem is to focus on this second order ODE, solve for y of t, and then take the derivative of y of t to find v of t. That is one way to think about what's happening here. However, since the primary unknown that we are interested in at this stage is v of t, there is another clever way we can another clever way to approach the problem here. Instead of writing everything in terms of y of t, I can actually write everything in terms of v, in terms of velocity, but there is something clever that we should do. So that was one approach. I'm not gonna follow this approach. I'm gonna do something clever. But this is all good. This is all very, very good. What I'm gonna do here is as follows. I'm gonna look at the problem I have. The problem I have is that here I have both v and y in my equation, both v and y, and I would like to have an equation that only has v in it. And to do that, I'm gonna do something clever. What I will do is as follows. So second approach, which is very clever, second approach, view v, the velocity as a function of y, as a function of height, instead of a function of time. At any height, you have a velocity as a function of y. No, so now let's see how this will work out. So if I'm viewing v as a function of y, here instead of having dy dt on the left, I should work with dv dy. And how can I compute dv dy? I can use the chain rule. We may use the chain rule. So this was the first approach. The first approach, the second approach. We may use this chain rule. We may use the chain rule. The chain rule to find a formula to find a formula for dv dy. Instead of having dv dt, I want to have dv dy. I want to eliminate t in a sense. Chain rule to write. So by the chain rule, dv dt is equal to dv dy times dy dt. Now, this dy dt is v itself, The derivative of y with respect to t is v itself. So this is equal to v dv dy. So dv dt is v dv dy. Let me call this 1, call that 2. Now I can write my equation with only v in it, but v as a function of y. It's not like I have v of t and y of t. I have v and y is my independent variable. V is the dependent variable, y is the independent variable. The problem with the previous version, the version 1, was that we had v as a function of t, y also as a function of t. Two functions. But now I'm going to view v as a function of y. That will be the only unknown for me. So 1 and 2, they will give me an equation for v, a first order equation for v in terms of, as a function of y. V dv dy is equal to negative g, the radius of earth squared, divided by y plus radius of earth squared. And so that is that. Now v is a function of y. This is a first order ODE for v as a function of y. First order ODE for v as a function of y. And what will be our initial condition? This is first order ODE. I have only one initial condition. V at 0, at height 0, time is also 0. Remember, at this 0 that you see here is height 0, y equals 0. But t equals 0 also corresponds to y equals 0. At time t equals 0, the projectile was on the surface of the Earth. So let me actually explain this here. Here I'm talking about the y equals 0. At y equals 0, v of 0 is v0, because at t equals 0, we have y is equal to 0 and v is equal to v0. Okay, all right, this is excellent. This is excellent. Now we have our initial value problem, and we want to, this is actually the end of like finding the governing equation for v. What I want to do now is that actually I want to, for this problem again, I want to solve this equation, and then that will help me in answering the multiple parts of the multiple questions that we had in the statement of the problem. But this even getting to this point is a big deal, right? And coming up with this equation using the Newton's second law. So the next step for me is to actually solve this initial value problem, find the formula for V. And to do that, as you know, first, I will ignore the initial condition. I will focus on the equation. I will find a general solution, and then I will apply the initial condition. So let me actually write this as usual. As usual, first, we find the general solution of the ODE, in the sense that we ignore the initial condition, and then we apply the initial condition to determine the arbitrary constant that appears in our general solution. So let's do the general solution. Let me change the color. General solution. So the question is that how to solve this ODE. V dv dy equals negative g re squared divided by y plus re squared. All right. And a little bit of a moment's thinking, I will tell you that this is actually a separable equation. So we can solve it using the steps that we have for solving separable first order ODEs. How to solve this? This is a separable first order ODE. Here we don't have constant solutions. We just need to separate the variables and then integrate. So I'm going to separate the variables. V dv is equal to negative g re squared divided by re plus y squared. Y plus re squared, re plus y squared, the same thing. And then dy here, and then I can integrate both sides. So integral v dv is equal to negative GRE squared is a constant. I'm gonna put it outside in the front, and then integral of 1 over the radius of Earth plus y squared dy. And this is a very simple integral. With a very simple substitution, you can compute the integral on the right-hand side. The integral on the left is also very easy. So what we have here is that 1/2 v squared, the integral on the left, we are viewing v as a function of y. V of y squared, that is on the left. And then on the right, the integral of 1 over re plus y squared is negative 1 over re plus y. So I will get g re squared divided by re plus y squared, and of course plus c. We know that when we are solving separable equations at this step, when we are integrating both sides, we need to put the constant of integration only on one side. Here I put the constant of integration on the right-hand side. All right, so very, very good. Now I have an expression for v of y. I'm going to apply the initial condition. to find C. Apply. Now we apply the initial condition to find C. So what was the initial condition? At y equals 0, v is equal to v0. So I know that at y equals 0, we have v of 0 is equal to v0. Here 0 refers to the fact that y is 0. So I'm gonna use the equation that I just obtained, and I will set y equals 0 on both sides. So we have 1/2 v of 0 squared is equal to g re squared divided by re plus 0 squared plus c. So 1/2 v0 squared is equal to one thing that I made a typo here. When you take the integral of 1 over re plus y squared, the answer will be negative 1 over re plus y. So we don't have a square there. So let me remove the square. And then g re squared divided by re will be g times re and then plus c. Perfect, perfect. This is really, really good. So that tells me that C is equal to V0 squared over 2 minus GRE. All right, now I can put everything back together. So that here I'm gonna call this formula 3. And then this C, I'm gonna call it 4. 3 and 4 will tell me exactly what V of Y is. So 3 and 4 together, 3 and 4 together. Now we found the answer to the first part of our question, which was about the velocity, determine the velocity of this motion. So this tells me that 1/2 V of Y squared is equal to GRE squared divided by RE plus Y. And then I have to add plus C. I have my C in 4. So it will be plus V0 squared over 2 minus G RE, the radius of F. I'm going to solve this for V of Y. So first I'm going to multiply both sides by 2. So this tells me that V of Y squared is equal to 2G, the radius of Earth squared, divided by the radius of Earth plus Y, plus V0 squared minus 2GRE. And so V of Y, I have to take the square root. And of course, it can be plus or minus, depending on whether it's rising, the mass, or whether it's falling back to the earth. If it's rising, we have the plus sign. If it's falling back to the earth, we have the negative sign of a square root of this guy, V0 squared minus 2GRE plus 2GRE squared divided by RE plus Y. This is the formula for the velocity of your projectile at height Y. So let me just be very also clear about the positive and negative sign. I told you about it, but let me write it. So this is V as a function of altitude. Here we have V, we have V as a function of altitude, Y as a function of altitude. The plus sign must be chosen if the body is rising. And the minus sign if it is falling back to the earth. So in a sense, we answered the first part of our question, which was about velocity. And now if you want to view it as a vector, that is also okay. You can view it as a vector. As a vector, that is actually very simple. As a vector, v of y is equal to vyj, as we discussed before, which is equal to plus minus the square root of v0 squared minus 2gre plus 2gre squared divided by re plus yj. Right? Again, j is the unit vector in the positive y direction. Or I think this completes our answer to the first part of the problem. And remember, the second part was about we want to make sure that the v0 is such that the maximum altitude is h. So what does that mean? We want to make sure that when we reach the altitude h, then the body starts falling back to the earth. And what does that mean? That means that we want the speed to be 0 at the altitude h. So this is how you answer the second question. If you want the maximum altitude to be h, that means that you want the speed to be 0 when the body is at altitude h. So that is how we can find h. So this is the answer. We are done with the answer to the first part. Now I'm going to answer the second part of our question. So the maximum altitude h is reached when v becomes 0. When the velocity becomes 0, that means that now the particle, the body starts falling back to the earth. So I'm going to use the formula that I have here. I want find our goal. So let me be very careful about this. So our goal is to find h such that v at h is equal to 0. So I have a formula for v. I'm going to use my formula. V at h being 0, that means they are equivalent. What I'm going to write on the left and the right are equivalent, but I'm going to just write the forward direction. V of h equals 0. It tells me that v0 squared minus 2gre plus 2gre squared divided by re plus y is 0. Okay, I want to solve for v0. That is the thing. I want to find the v0, the initial velocity that ensures that the maximum altitude is h. So I want to find v0 from this equation. So let me bring the last term to the right side. So this what this tells me, or let me bring the first two terms to the right, leave the last term on the left. This tells me that 2gre squared divided by re plus y is equal to 2gre minus v0 squared. Okay, so far so good. And then, so and y is h. I just realized here y is h. Y is h. I want to determine a relationship between v0 and h. I want to know what h is in terms of v0. And later I'll build what v0 is in terms of h for part 3. Right? That is the key here. Like we want to find the relationship between h and v0. Okay, so in a sense, let me, and as a matter, I want to solve for h here, right? So assume that v0 is given. I want to see what the maximum altitude is, and then later I can see that if the maximum altitude is supposed to be h, what the v0 will be. Both are valid, good questions. All right, but this part I should stand corrected. This part we want to, the v0 is given, and I want to determine the maximum altitude h, the corresponding maximum altitude h. So I have to solve for h. So this tells me that r E plus H is equal to 2G RE squared divided by 2G RE minus V0 squared. And this tells me that H is equal to 2G RE squared divided by 2G RE minus V0 squared minus RE. And I'm going to compute the common denominator. So this will be 2G RE squared minus 2G RE squared plus RE V0 squared divided by 2GRE minus V0 squared. And clearly, this guy and that guy cancel. And so we can conclude that H is equal to RE V0 squared divided by 2GRE minus V0 squared. So since here I solve for H, this tells me that if the initial velocity is V0, the maximum altitude that you will get is RE V0 squared divided by 2GRE minus V0 squared. And of course, I can do it the other way. I can actually solve for V0 in terms of H. And then that tells me that if I want the maximum altitude to be H, what should be the corresponding V0? And I need to do that, as a matter of fact, for part 3. So part 3, let me answer part 3 of this exercise. Part 3 is about the V0 that will ensure that the maximum altitude is infinity. There will be no finite maximum altitude. And for that, let me use this equality, solve for Y0 in terms of H. And then I can do the analysis needed for this part of the exercise. So I'm gonna say that H is equal to RE V0 squared divided by 2GRE minus V0 squared. So that means that I can multiply the both sides by the denominator of the right-hand side. So I will get 2GREH minus HV0 squared is equal to REV0 squared. And then that tells me that I'm going to bring all the V0 squared terms to the right. 2GREH is equal to H plus RE times V0 squared. And that tells me that V0, which is necessarily a positive number because we are shooting this upward, shooting the body upward from the surface of the Earth, V0 is equal to a square root of 2GREH divided by RE plus H. So now we have it both ways. I have H in terms of V0, the maximum altitude in terms of V0, and now I have V0 in terms of the maximum altitude H. If you want the maximum altitude to be H, the corresponding V0 is obtained by this formula. And of course, now in this part of the exercise, I want the maximum altitude to be infinity in a sense. So let me actually write this down. So the escape velocity, let me denote it by the VE subscript. The V0 that gives me the maximum altitude infinity, in a sense, I'm going to call it VE. The E stands for escape velocity. VE is determined by letting H go to infinity in the above formula. So what we have is that VE is the limit as H goes to infinity of a square root of 2GRE H divided by RE plus H. And what is that equal to? Very simple, because this a square root of 2GRE that doesn't have any H in it. This is a square root of 2GRE and then limit as h goes to infinity of a square root of h divided by h plus re. And as h goes to infinity, this re becomes negligible. H over h will give me 1. This, you know from calculus 1 that this limit is equal to 1. So the escape velocity is equal to a square root of 2gre. That is the escape velocity. This is like the scalar version of the scalar velocity. As we discussed, where you can think of the vector version. The vector version will be a square root of 2gre times j. Or now, what is this quantity? What is this velocity that will ensure that the maximum altitude is infinity? The body will not return to the surface, will not fall back to the earth. So we need to know what g is, what the radius of the earth is. The g, you all know the value, at least in the SI system, it's about 9.8. And the question is, what is the radius of the Earth? Let me actually tell you the values, some of the values that constants that we had in this problem. So the radius of the Earth, you can also Google this, the radius of the Earth, this RE is approximately 6.37 times 10 to the power of 6 meters. And then the mass of the Earth is approximately 5.98 times 10 to the power of 24 kilograms. And that universal gravitational constant G, the universal gravitational constant, big G, gravitational constant. These are the constants that we saw during our solution. Is G is approximately equal to 6.67 times 10 to the power of negative 11 Newton meters squared, kilograms squared. Okay, over kilograms. Okay, so these are the constants. Now, if you use these values, this square root of 2gre is approximately 11.2 kilometers per second. So if you shoot your projectile, your body with this particular velocity, it will not fall back under the assumption, simplifying assumption that we had here. It will not fall back onto the surface of the Earth, Very good, very good. I think we answered all parts of this question.